And I want to just quickly just tell you about the domain rules. Yeah, on the natural log logarithms. Yes, so just a little just jot something here real quick. When you see that, so natural log of 5, for instance, all that means is that I have log base e of 5, just like if you see log of 5 with no base written, that's log base 10 of 5. Natural log, I said in the video too, we literally use it because it's fewer characters and it's in cursive. There's really no reason other than simplicity that natural log kind of takes on this. It just becomes our default log to use when we're trying to get the power rule working for us. All right. So how do logarithms work? The old denominator rules, old division by zero rules and variable under even root rules apply when I have a domain. But now that I have logs, logs are not allowed to have an argument that is negative or 0. So when I look at a function, because right here is f of x, log base 8 of quantity 4 minus 6x, first rule, does this have any variables in the denominator? No, there's no denominator. Does this have any variables in under an even root? No, there's no even root. And then now the third question is there a variable inside the argument? Yes, there's almost always going to be one inside the argument. The argument must remain greater than 0, not greater than or equal to, greater than 0. I cannot have I can't take log 8 of 0 because there's no power I can raise 8 to get 0. So that's why to find the domain, I need to take that argument, set it greater than or equal to 0 and solve. Add 6x to both sides and divide by 6. And I'm going to find x. I'm going to find 4 6 is greater than x, which I can turn around. Say x is less than 4 6, right? The pointy side of the greater than still points towards the x. The open side points towards 4 6. That's the technical terms here. And 4 6 reduces to 2/3. So what is my domain? It's everything less than 2/3. In interval notation, that's negative infinity up to 2/3, not including it. Right? And if you get one of these problems and it has a variable in the denominator, it has a variable under an even root, you have to take all those rules, the old rules, into account as well when you're finding domain. All right. Now, a key feature of logs and exponents, because they're inverse functions, and they have an equality. And we kind of talked about how log base b of a equals y literally means what power do I raise b to get a. So that means I can go between exponential form and logarithmic form. And that's a really important feature. So for instance, 3 squared is equal to 9. So log base 3 of 9 is equal to 2. Those are equivalent statements. What power do I raise 3 to get 9? 2. What power do I raise 3 to get 9? 2. So we're going to do the same thing, just kind of swap between them. 4.3 raised to the k is equal to 80. The base is 4.3, okay? And then if you're trying to follow along here, take a look at, I'm in exponential form, I'm in this by is equal to a form. B becomes the base of the log. A becomes the argument. What is A? A is the number on a side by itself that's not raised to a power. So that's 80. And then that equals k. What does 4.3 k equal 80 mean? Or how do I solve that for k? What is k here? It's the power I have to raise 4.32 to get 80. Okay. Next, we'll go the other direction. Log base x of 19 is equal to 1.2. Rewrite that in exponential form. The x is the base of the log. The x is the base of the left-hand side. The 19 is inside the parentheses for the log. It's on the other side of the equal sign in the exponential form. And then the 1.2 is y, and that is the power that I raised the base to. What power do I raise x2 to get 19? 1.2. What power do I raise x2 to get 19? 1.2. All right, same thing. Base is 4. The power equals the argument is the 64. What power do I raise 4 to get 64? P. 8 to the negative 2 is equal to a. Again, following, and once you do these, I mean, you're still gonna, if I'm being totally honest, I still have to kind of go back and refresh myself on these. So whenever you go to take the test, jotting down the translation between exponential form and logarithmic form is a great thing to do. But next, 8 to the negative 2 is equal to a. Well, let's just follow the pattern here. 4 to the p is 64. Where does that 4 go? It's the new base. Okay, well, in this problem, 8 is the base. Where does that p go? Oh, it goes on the other side of the equal sign. Okay, what do I have where the p is in the problem above? Negative 2. And then where does the 64 go? It goes inside the argument of the log. And that is the letter A. So that means I have log base 8 of A equals negative 2. What power do I raise 8 to get A? And then the last two, 10 cubed is 1,000. This is just a statement, right? That's a true statement. 10 times 10 times 10 is 1,000. But it is in exponential form. I can rewrite this as a log. Well, that's log base 10 of 1,000 equals 3, right? The 10 goes to here, the 1,000 goes to the argument, and the 3 goes to the right-hand side. That is the common log. So when log base 10 is appearing, you actually don't have to write the base. It's the only time that you don't have to write the base. Log base 10 is the common log. And that matters because if your TI-30 or TI-36 calculator cannot do logs that have other bases. It is relegated to only logs that are common logs and natural logs. All right, same thing, e to the 3.4 is equal to m. Rewrite that in logarithmic form. E is the base, m is the argument, 3.4 is the solution. Log base e is the natural log. It's the natural log. So this is the other one where you don't have to write a base here because the fact that this is a natural log tells me the base is e. All right, what power do I raise e to get m? And the answer is 3.4. Notice I didn't solve anything here, right? I didn't solve any of these problems. I didn't do anything. I just translated them between logarithmic form and exponential form. What do I mean when I say that? Exponential form means I've got exponents. Logarithmic forms means I have logs. All right. So let's think about some of these problems and see if we can do these without a calculator first and then with a calculator second. Again, these are just things you're going to be plugging in on the right, but down the left-hand side, let's think about these logs. And the first one should jump out as pretty easy. Log base 4 of 16. What do I raise 4 to get 16? 2, right? 4 squared is 16. What do I raise 2 to get 1/8? That one may not jump off the page at you. So it never set well with me that they would say, okay, we'll convert this to exponential form. Well, exponential form has an equation, right? It has variables on the left. It has numbers on the left and numbers on the right. So if I'm going to convert this, I need to say log base 2 of 1/8 is some number x. Now convert this. Convert from logarithmic to exponential. That says 2 raised to the x power is equal to 1/8. This looks like a problem we've done before, right? If I can get the bases to be the same, I can find my answer. Well, the 8 is in the numerator. I don't really like it down there because it doesn't do me any good. So I bring it up to the denominator. 8's in the denominator. Bring it up to the numerator by using the negative power. And then what I want is the same base. Well, 8 is 2 cubed, right? So if 2 to the x is equal to 2 to the negative 3, then x equals negative 3. If you saw that from the beginning, that's completely doable in your head. Great, keep up the good work. If not, write it out. There's nothing wrong with it. Natural log of e. Remember, this means natural log means log base e of e. And whenever the base and the argument match, the answer is always 1. Next rule, this is the common log. Remember, let me go under it and write that because that might be confusing. Because it's a common log, the base is 10. Getting the base and the argument related is always a great idea if you can. So that's log base 10. 1,000 is 10 cubed. And anytime I have the base and the argument with the same base, the answer is the exponent. What power do I raise 10 to get 10 cubed? 3. And then lastly, next to last, the penultimately, log base 2.35 of 1 is what? This one I'm going to take and go ahead and give it a right-hand side and then convert. This says that 2.35 raised to the x power equals 1. The only way that's possible is if x equals 0. Exactly. X has got to be 0 because anything to the 0 power is 1, excluding 0 to the 0, but you're not going to run into that. And then lastly, we're going to reiterate what I said earlier. When I get the bases to match, the exponent then becomes the answer. Log base 7 of 7, well, that's log base 7 of the square root of 7 can be rewritten as 7 to the 1/2 power. When the base of the log and the base of the argument match, the answer is the exponent. All right. What power do I raise 7 to get 7 to the 1/2? 1/2. All right. So, got those. And now down the right side, it's really no point. Like I said, these are in the video. You're literally just plugging numbers in to get the numbers on the right. So don't, just jot. You'll just be able to go into your calculator and do that. Log of 15, this is the common log. And what I'd want to see here is this is 1.176. And it is rounded. That's why you see me use the little squiggly equal sign to let the reader know that it's an approximation. So this is the common log. 10 raised to what power gives me 15? 1.16. Log of 0.343. Think about that one for a second. What do I raise 10 to get 0.343? Well, it can't be anything greater than 1 because 10 to the first power is 10, and this is less than that. So when you plug this in, you're actually going to end up with a negative answer. And that is fine, because what does that negative answer mean? That means 10 raised to the negative 0.465 is equal to 0.343. A log can give you a negative number. That's absolutely fine, but you cannot take the log of a negative number, and you cannot take the log of 0, right? The argument always has to be a positive number. Basic properties, we've already touched on these. Log base b of 1 is 0 because b to the 0 power always equals 1. Log base b of b is 1 because, and this is a little more clear here, what power do I raise b to get b? Well, that b in the argument is technically b to the first, right? So power, base, and the argument have the same, base and the argument are the same number, then the result is, the answer is the exponent. Log base b of b to the x is x, right? If the base and the argument have the same base and the argument has an exponent, the answer is the exponent. And then lastly, I'm not going to quiz you on why this happens. I just want you to see it. If I have a base and I raise it to the log of that same base, the answer becomes the argument. B to the log base b of x equals x. So let's just do a quick run through of evaluating these. They're going to have the same answer. You'll pick up on the pattern pretty quick. Log base 3 of 1. Well, what power do I raise 3 to get 1? Anytime the argument is 1, the answer is 0. What power do I raise 16 to get 1? 0. 144 to the first, 144 to 1, 0. Next, the base and the argument match exactly. What power do I raise 3 to get 3? 1. What power do I raise 16 to get 16? 1. 144 to get 144? 1. And now we're going to see this third property. If I have the base and the argument have the same base, and I have a power, the answer is the power, because what's this question? 3 raised to what power gives me 3 to the 7? 16 raised to what power gives me 16 squared? 144 raised to what power gives me 144 to the negative 1? And then the last one, when the base and the base of the log match, the answer is the argument. All right. So there's a set of problems down here. They're exactly the same. They're in the video. I don't want to spend any more time on it because I want to get to the properties. All right. So what is 3.4? 3.4 brings in the properties of logs, which this is what we're going to use to solve logarithmic equations. If I have multiplication, so if I'm taking log base b of m times n, that can be rewritten as log base b of m plus log base b of n. You've never seen a property like this before, where multiplication on the inside corresponds to addition on the outside. If multiplication corresponds to addition, then division has to correspond to subtraction. And then lastly, log base b of m to the p is equal to p times log base b of m. What in the world did I just do there? The power property, or the power says, if you have the log of something raised to a power, then you can bring that power out front and it becomes the coefficient of the log. Log base b of m to the p is equal to p times log base b of m. All right, this one is a key property. This is going to be the one we're using because exponential equations, which we're going to be there soon, Exponential equations are equations where x is in the exponent. This power rule, power property, is going to be the reason or the way that we solve those equations, because this is the only thing that allows us to get that variable down. So let's deal with some practice here, see if we can rewrite. So the first two here, I have a sum of logs and a difference of logs. I'm going to rewrite these using the properties. Well, this is a sum on the outside. The product property says that if I have addition on the outside, I can rewrite that as multiplication on the inside. 1 base 3 of 7x. Okay. Now the property, yeah, x7, and then I just rearrange it because you're used to seeing the coefficient first and then the variable second. So I didn't put parentheses here. It's just to show you, you don't have to have them unless there's multiple terms in your argument. I try not to use them as much, but like I said, I was trained by somebody that taught me to do this over and over again. Parentheses go everywhere. So log base 3 of 7x. How about subtraction? Well, this is the quotient property or quotient rule. I can still use that because you haven't hit calculus yet. The quotient, well, if I could spell property, it would be super helpful. Quotient property says subtraction on the inside is the same thing as subtraction on the outside is the same thing as division on the inside. All right. Now, notice both of these problems, the base of the log matched. Log base 3 of x, log base 3 of 7, log base 3 of x, log base 3 of 7. I can only use the product property if I have the same log, same base in both terms. All right. Now, let's go the opposite direction. Or actually, this one's actually expanded. I have 7 times log base 3 of x. The power rule says that if I have the log of something raised to a power, I can bring that power out front. Go the other direction. That means if I have a coefficient, I can bring it inside, and this becomes log base 3 of x to the 7th. Okay. These properties, like I said, they run both directions. If I have the log of something to a power, I can bring the power out front. If I have something out front, if I have a coefficient of my log, I can bring it back inside and make it my exponent. Next, natural log of 3 times a. This is the product property. I have multiplication on the inside, which means this becomes addition on the outside. And then log of 5 over a, this is the quotient property. Quotient property says the log, if I have division on the inside, I get to rewrite that as subtraction on the outside. And then lastly, the power rule one more time, power property. Power property says if I have the log of something raised to a power, I get to bring that power out front. And then what I'm left with is log base 6 of whatever was raised to that power. Notice the -2, when it goes out front, it stays out front. We don't rewrite a to the -2 in here. That -2 went out front, and that's that. All right. So you've seen these as, again, these are basic examples, but they're good because you've seen this in both directions now. You have seen a case where I have everything written as one log and I break it up into multiple logs, and you've seen a case where I have multiple logs and I consolidate them into one. All right, so let's do some practice. All right. So I'm asked to rewrite the logarithmic expression as a sum or difference of simple logarithmic terms, express all the powers as products. We can do that. That's easy enough. Log base 3 of 7x squared. All right. Now this one starts out easy, and that's what we want. We have to deal with what's the most outer property, or what's the most outer, what property can I use first? If I had the log of something raised to a power, I could bring the power out front. Problem is, this square is not applied to everything in the parentheses. It's just applied to the x squared. So I can't use the power rule yet, but I do have multiplication on the inside, 7 times x squared. So using the product property, I can rewrite this as log base 3 of the first factor plus log base 3 of the second. And now I have log base 3 of something to a power. So now the power rule or property is going to let me rewrite that second term as 2 times log base 3 of x. All right, these are compound exercises like the gym, right? You want to work your lats and you want to work your chest and arms and as many muscle groups as you can, so that one exercise gives you multiple processes, or it works multiple muscle groups. Same thing here. To break this up, I need the product, but then when I come down here, now each of these, I can, if the product, quotient, or power rule come into play, I can do those again. All right. How do I know I'm done? I'm done when the argument no longer of any log no longer contains products, quotients, or something to a power. Okay. Next, I have the natural log of, and I'm gonna I remember coming up through math, and I was always very confused if the notation wasn't perfect. That is the natural log of 2x plus 3 divided by x squared plus 3x plus 2, close quantity cubed. So I do have the natural log of something raised to a power, right? So you can see a couple of things going on in there. You can obviously see division, so the quotient rule comes into play, and you can see the power rule. Which one of those is working first, or which one of those am I going to have to deal with first? I keep saying can't. I have the log of something raised to a power. So ignore the fact that this is a whole bunch, this is, linear expression and a quadratic expression. And just say this is the natural log of something raised to a power. So that means using the power rule, I can rewrite this as 3 times the natural log of 2x plus 3 over x squared plus 3x plus 2. All right, next. All right, well, now I have the natural log of a quotient. I have a numerator and a denominator. So now the quotient rule says that I can rewrite this as 3 times the natural log of the numerator, division on the inside, corresponds to subtraction on the outside. All right, that 3 needs to be distributed to both of these, right? That's 3 times the natural log of this quotient. I've broken up this natural log into the subtraction of 2 terms. Fine, but that 3 better go along with everything. So that's 3 times the natural log of 2x plus 3 minus 3 times the natural log of x squared plus 3x plus 2. What else can be done here? Okay. Well, nothing jumps out. There's no products sitting in here. There's no quotients sitting in here. There's a power. So I have a quadratic over here. Can I can't do any more with the first one, but can I do something over here with this x squared plus 3x plus 2? Yeah, that is a quadratic that factors. Why is that a useful feature? Because if I have the log of things that are multiplied, I get to break it down into plus the first plus the second. X squared plus 3x plus 2. Two numbers that multiply to 2 and add to 3 are 2 and 1. Well, now this is the product property. Product property says if I have the log of two things that are multiplied, I can rewrite this as, notice the first term is not changed in 4 steps, okay? Minus 3, and then here I am using my brackets again, times the natural log of the first factor plus the natural log of the second factor. Distribute, and I end up with 3 times the natural log of 2x plus 3 minus 3 times the natural log of x plus 2. That is minus 3 as the natural log of x plus 1. Can I do any more with this? Are there any more powers, products, or quotients inside the parentheses? Nope. Do any of these logs have the exact same argument? No. If they did, they would be like terms and could be added together. But none of these do, so we don't have to worry about that. Now, here's the thing. It looks daunting. This looks a little scary. But I want you to see the math that we're actually doing here. Each line where we use one of the new properties of logs, I wrote it. So power rule got the exponent down. Quotient rule broke up this log. The product rule allowed me to break up this log. Everything else is distribution. It's just multiplication, addition, and subtraction. Okay, so as you're doing these problems, if you get them and you just get overwhelmed with it, take a step back and just look. This step, so this process right here from the natural log of a product to 2 natural logs, the sum of 2 natural logs, this quotient, this division to subtraction, and then bringing that 3 out front. Those are the only new math that you're getting exposed to now. Everything else is just old school algebra. So let's keep going. Over here on the left, I have the log of the square root of 5x. Right? Last time we had this, we had a power that when we had log of something in here, the one up above, I had 2 things multiplied and the power only applied to one of them. In this case, that's not it, because the square root of 5x is the same thing as 5x to the 1/2 power. Why is that good? Because the power property says if I have something raised to a power, if I have the log of something raised to a power, I get to rewrite this as the power times the log of whatever the base was. Excellent, right? So bring the 1/2 out front, and now I just have 1/2 times the log of 5x. Well, this is a product. So I have 1/2 times the log of 5x. It's 1/2 times the log of the first factor plus log of the second factor. And then distribute. That's 1/2 log of 5 plus 1/2 log of x. Can I do any more with this? Are there quotients, products, or powers inside my logs? Nope. Do any of my logs have the same argument? No. Then I'm done. Okay. Again, 2 steps here. Bring the power out and then break it up. Those are that's the new math. Everything else is old math. All right. Getting comfortable rewriting roots as fractional powers, that comes with time and practice. And that's why I'm trying to get through as many examples as I can, because that's what I want you working on between now and the next class is practice, practice, practice. 3, 4, and 3, 5. All right, so the next, let's come over here and deal with this natural log of e to the x. There's a product on the inside, so that means I have the natural log of e plus, no, you do not need to do that. So Tony had a good question. When you're doing this work and submitting it, do you need to indicate which property you're using? No, I'm cool with you just going straight from this to this step without mentioning it. Right? But if you want to, you can. Now, take a look. I only use one rule here, but there's something else that can happen. Remember what natural log is. Natural log is log base e. What happens when the base of the log and the base of the argument are the same? The answer is the exponent. What power do I raise e to get e? 1. So log base e of e, or natural log of e, is just 1. Why can't I do anything with the natural log of x? Because the base is e, and I can't rewrite x in terms of e. X is just x. All right. Down to the left, I have a very similar setup. This is going to work very similar to the very first problem we did. Because in the first problem we did, I had the log of 2 things that are multiplied. One of them had a power, one of them didn't. So what's the first property I can use? It's the product. I don't have the log of one thing raised to a power. I have the log of something times something raised to a power. So let me break it up using the product rule, which says I can break this up into the natural log of x plus the natural log of e to the x. The first term is done. The second term then allows the power to kick in. So what have I got now? I have the natural log of x plus, bring the power down, and then rewrite, and then write the natural log of the base. And we have the same situation we just saw. Natural log of e is 1. So that means I have the natural log of x plus 1. Plus 1 what? That's a 1. There's still an x out here. So that's the natural log of x plus x. Sorry, I took a little nap there in my head and forgot about the x that was still there. All right, the natural log of e is 1, but it doesn't impact that x out front. 1 times x is x. All right. Let me take a breath here and pause. Any questions? Again, questions typically come when you do these problems. I know how homework and math works. It's hard. Once you sit down to focus on it, you can really get into it. But if you haven't been watching the videos and doing these, I know the questions. You're mainly just trying not to drown for the next 30 minutes, and then you'll go figure out what's hard and what's not when you go to do your assignments. All right. So next, log base 2 of quantity x cubed divided by x minus 3. what's my outermost operation here? Is it multiplication, is it division, or is it a power? Okay. Well, I have log base 2 of whatever I'm taking the log of, that entire thing is not raised to a power. The numerator is, the denominator is not. So that means the power rule is not the first rule I can use here. Instead, the first rule I can use here is the quotient rule. The quotient rule says if you have division on the inside, it corresponds to subtraction on the outside. So log base 2 of x cubed divided by x minus 3 is log base 2 of x cubed minus log base 2 of x minus 3. And then the power rule kicks in because that first term has something to a power. So log base 2 of x cubed is the same thing as 3 times the log base 2 of x minus, and the second term is not impacted. Is there anything left to do? Nope, because I'm drawing a square around it, right? Nothing left to do because on the inside of my logs, I do not have multiplication, division, or something to a power, so I can't do anything else. There is a temptation here, I think this is the first time, one of the first times you've seen, where an argument of a log has addition and subtraction inside the parentheses, and you and every other person that's ever taken math is going to be tempted to say, oh, subtraction on the inside is division on the outside, and you think you can keep going. You cannot. Division on the inside corresponds to subtraction on the outside. It cannot go the other direction. It cannot be subtraction on the inside is division on the outside. All right? And then we have this last one, which looks like a mess, right? I have the natural log of 5x squared times the cube root of 1 minus x, all divided by 4 times quantity x plus 1 closed quantity squared. And what is this out here to the right for x, for 0 less than x less than 1? This is the domain. They had to tell us the domain here because this function doesn't have an output for a lot of x values, for most of the x values. Now, what is my outermost function here? I have the log of, I don't have the log of a product or a quotient raised to a power. I have the log of a quotient. So the quotient rule says that the natural log, if I have division, I can rewrite it as subtraction on the outside. So that's the natural log of the numerator minus the natural log of the denominator. And then what? Well, the product rule comes into play. So what have I got here? Well, I have the natural log of 5x squared times the cubed root of 1 minus x. I'm not going to do a property or a step here for properties, but I am going to really point this out. That's 5 times x squared times the cubed root of 1 minus x means 1 minus x to the 1/3 power, right? The index of the root is the corresponding denominator. And then that's minus the natural log of 4 times x plus 1 squared. Why am I drawing the times out? Because I want you to see that there are 3 cases of the product rule here. The first is a product times a product times a product, or excuse me, a factor times a factor times a factor. And then in the last one, I have a factor times a factor. So I can use the product rule to break this up. So the first one is the natural log of 5 plus the natural log of x squared plus the natural log of, I'm going to do brackets here so that we don't have parentheses overlapping. 1 minus x to the 1/3. So that's the entire first term. That natural log of the numerator got broken up into 3 additions, right? Use the product rule 3 times. Minus, and then you know me, if I have a minus or a coefficient and I'm gonna break something up into multiple logs, I'm gonna put a big old bracket here to remind myself to distribute. 4 times the quantity x plus 1 all squared, it's broken up into the natural log of 4 plus the natural log of, again, just to be consistent or just to try to really drive a point home here. Natural log of 4 plus the natural log of x plus 1 squared. Notice this subtraction has to be distributed to both. So that means I'm looking at the natural log of 5 plus the natural log of x squared plus the natural log of 1 minus x to the 1/3 minus the natural log of 4 minus the natural log x plus 1 squared. All right, so product rule, and then distribution. Now, what else do you see? There are no more products on the inside, right? But there are logs of stuff raised to a power. Natural log of x squared, natural log of 1 minus x to the 1/3, natural log of x plus 1 all squared. So I've got 3 cases of the power rule, which means what? I get to bring it out front. So I now have the natural log of 5 plus, the power rule says I get to bring the power out and treat it as the coefficient, plus 1/3 times the natural log of 1 minus x. I drop the brackets because I'm taking the natural log of 1 minus x. It's not the log of something raised to a power. So that's why the brackets are here, just to drive home the point. I'm taking the natural log of 1 minus x all to the 1/3. It's not taking the natural log of 1 minus x and then the answer or the result gets raised to the 1/3. So that's why you see me do brackets and parentheses. Minus the natural log of 4 minus, power rule again, 2 times the natural log of x plus 1. Okay. And here I go again with my rectangle, which must mean we're done. Go down your list of things. Are there multiplication, division, or something to a power inside any logs at the end of this problem? Nope. And that means we did it, and we did it right. All right. So we have taken a single log and written it as a sum and difference of simple logs. And now we're going to be asked to go the opposite direction. There's four examples left here, then we jump over to 3, 5. So we've expanded a single log into multiple logs. Now we're going to take multiple logs, sums and differences of logs, and compress them into a single log. So how about log base 6 of 9 plus log base 6 of 4? I don't know any numbers that jump off at what do I raise 6 to get 9, so I can't really replace this with a number. Same thing here. So what can I do? Well, I have addition on the outside, which is the product rule. It's just in the reverse of the way we're using it on the last page. Addition on the outside means multiplication on the inside. Log base 6 of 9 plus log base 6 of 4 is the same thing as log base 6 of 9 plus 4. What is 9 times 4? It's 36. And what do I raise 6 to get 36? 36 is 6 squared. This is 2. Okay. So even though I can't see, or I don't see the answers here to what is log base 6 of 9, what is log base 6 of 4, by consolidating them to a single log, I ended up creating an equation that I was able to solve completely. All right, so that comes out at 2. Next, natural logs, and I've got them subtracted. This is the quotient rule. It says if I have subtraction on the outside, I can rewrite that as division on the inside, x minus 2 over 2x plus 5. Okay. This one didn't break down to a single number, and that's absolutely fine. It also didn't, the first one didn't have a variable in it. So if you're wondering why the answer to the first one is 2 and the answer to the next one is, I just wrote it as one natural log with a quotient inside. It's just dependent on the problem. If x is in there, you're probably going to end up, you're most likely going to end up with a single log that still has terms in it, or still has stuff in the argument. If it doesn't, like this one on the left, you probably won't. E to the natural log of 7. Okay? There's nothing about this one. There's no product or property rule, or none of the 3 rules are going to apply here, because that is e, just remember, raised to the log base e of 7. Whenever the base of the exponent and the base of the log match, and you've got one raised to the other, you get the base of the exponent raised to the log with the same base, the answer becomes the argument. Okay. In the opposite direction, if I had like the natural log of e to the 7th, the bases would be the same, so my answer would come out to be 7. Okay. And then last one, I have 2 times log of x plus log of x minus 1. Now, the rule says there's 2 rules that can be applied here. One of them is obvious, it's the product rule. If I have logs that are added together, then I can rewrite them as the log of the first argument times the second argument. But I have a coefficient out front. And notice the rule, log of A plus log of B is log of A times B. Notice the rule doesn't have coefficients, right? This is not, I can't have like 3 logs of A and 1 log of B, right? So I can't apply the product rule here, even though it looks like that's what I want to do. What I need to do is deal with this coefficient first. It's throwing everything off. Well, the power rule says that if I have a coefficient, then I can rewrite that coefficient as the power of the argument. And now I've got the sum of 2 logs with the same base. Now I get to apply the product rule. The product rule says that I can take the sum of logs, and rewrite it as the log of the product of the arguments. I don't know which one they would want this in, so You can distribute the x squared or not. They both lead to the same answer. All right. Okay. The silence is deafening here. I know I can tell everybody's absorbing and wondering how they're going to do this homework in time. You're going to be fine. It comes with practice and time, and that is up to you. We have two sections after chapter 3, 8.1 and 8.4. Those are linear equations and nonlinear equations and systems. So I'll have those videos up before next week. You're going to remember the stuff from chapter 8. Don't worry. Don't let the fact that there's more coming worry you, because that's the old stuff. That's solving systems of equations. You've seen that. All right, so that's 3.3 and 3.4 knocked out. We have 15 minutes left. Are we sure there's no questions? All right. So if there aren't, I want to start into 3.5. Yeah, it is. Yeah. Yes. What is your question, Tenny? They're natural versions of the normal logarithm problems. They're all the same. So that's an excellent question. So every log, no matter what the base, as long as it's allowed, has those same properties of the product rule, the quotient rule, and the power rule. So you could have log base 7, you could have log base pi, you could have log base e, which is the natural log. Any base you want, logarithm rules always apply. Okay. Now the first page, if there's more, keep typing. I'm just gonna mention real quick. The first page of 3.5 is a repeat, and you've seen this. If I can get the same bases on both sides, I can make the exponents equal. This is from 3.2, so you'll see that in old videos. So we're gonna skip those. These are done in completion in the videos, or they're done in completion in 3.2. What I want to do is get over here to steps for solving equations, exponential equations using logarithms. Okay. So I have 2 minus 3 times e to the 0.4x is equal to -7. I want to solve this. Solve for x. That's the goal. The goal is to get x on a side by itself. So if you have an exponential equation and your variable is stuck in a power, which is the definition of an exponential equation, if I want to solve for it, I'm going to follow these 4 steps. The first thing I'm going to do is isolate the exponential expression on one side of the equation. The exponential expression is, in this case, it's the e to the 0.4x. The left-hand side and the right-hand side of the equation are expressions, and then when we throw the equals in the middle, it becomes an equation. So I want to isolate this e to the 0.4x. So let's do that, step 1. So everything, or really not just, it's just this e to the 0.4x needs to be by itself. Well, this 2 out here isn't doing me any good, so I'm going to get rid of it. It's preventing me from being having e by itself, so 2 minus 2 is 0. So on the left, I still have -3 e to the 4/10 x. And on the right, -7 minus 2 more is -9. E to the 0.4x is not by itself. because it's multiplied by -3. So I'm going to divide both sides by -3 to get that exponential expression by itself. And then -9 divided by -3 is 3. So now I have my exponential expression on a side by itself, which is exactly what I wanted. Second step, take a logarithm of the same base on both sides of the equation. This is going to default, this will typically be the natural log. And the reason is, like I said, it's easier to write. And then when you get to the final answer, if you have natural logs, you can use your calculator to do them. If I chose to do log base 7 on both sides here, I would end up with a number that I couldn't calculate in my calculator. So step 2 is to take the same log, or take a log of the same base on both sides. Why am I doing this? The reason I'm doing this is so the power rule comes into play. Step 3 is all about, so remember the goal is to get x on the side by itself. That's the long-term final goal. X is currently in an exponent. The only way I know to solve equations where my variable's in the exponent is to get the same base on both sides. E to the 4/10 x equals 3. E and 3 are never going to be able to be rewritten. Like 3 is not e squared or e cubed, and e is not 3 to some power. So I'm not going to be able to get equal exponents or equal bases to make equal exponents. So I need to get that x out of the numerator, or out of the exponent. I can do that using the power rule, because the power rule says that the natural log of something to a power is equal to that power times the log of the base. On the right-hand side, nothing changed. And I have 4/10 x times the natural log of e is equal to the natural log of 3. The natural log of e is 1. So that means I now have 4/10 x times 1 is just 4/10 x is equal to the natural log of 3. And then the last step, solve the resulting equation. X is times 0.4. I want x by itself. And there it is. X is equal to the natural log of 3 divided by 4/10. If you're scrambling for a calculator or Desmos to write that down in, please don't do that. Leave this as an exact answer. The reason for that is you can check these by hand as long as your answers are exact. If you round, if you do natural log of 3 divided by 4/10 in a calculator and then round your answer, if you go to plug that back into the original to check it, you're going to get inequality. You're going to get it. It's going to look like, well, that's not a solution. Okay. Now, for me, I have no desire to force you to do this check by hand. So I'm going to check x is equal to natural log of 3 divided by 4/10. And you've seen me do this before using Desmos. So what I do is I go back to the original. And the original is 2 minus 3e to the 0.4x is equal to -7. So I let the left-hand side be f of x, 2 minus 3e to the 0.4x. And then the right-hand side is -7. All right. Now, if I were to do this by hand, I would be plugging in a value for x and then solving, or I'd be breaking that down, multiplied by 0.4 raised to the e times 3, all that stuff. Since I've got my left-hand side and right-hand side up here, what I want to do is I want to find out, do f of x and g of x equal each other when x is the answer that I'm checking. So are f of x and g of x equal when x is equal to the natural log of 3 divided by 4/10? Let's find out. So what is f at the natural log of 3 divided by 0.4? Well, it's -7. Do the same thing for g and literally copy and paste, just swap out that f for a g. And we find that when I plug in natural log of 3 over 4/10 and that to f and g, the left-hand side and the right-hand side, both return the same value. That means this is a solution. So I'm going to insert that screen clipping. So there's my check. The check is not something I have to see. I don't expect it. It's a thing, it's just a thing at the end of the problem that will help make sure you don't give, you don't end up saying this is a solution when actually it's not. All right, so I'm checking natural log of 3 divided by 4/10. This checked, so that means my solution set and I'll tell you what, I'm gonna write that a little bit closer to the original problem, just as good practice. My solution set contains the natural log of 3 divided by 4/10. Again, leave it in its exact answer. Don't change it. Don't round it. All right. Last one, if you need to go, I understand. I will finish, I'll do this problem to its end, and then I will stop the video and get this up as well. I have 2 to the x minus 5 is equal to 0.75 raised to the x. Now I have 2 exponential expressions. I have an exponential expression on the left, 2 to the x minus 5, and I have an exponential expression on the right. Thanks, you two. So what do I do? Well, I can't isolate the exponential expression because there are 2 of them, but I certainly don't want to bring them both to the same side and then try to take a log. So instead, we're going to ignore step 1 because I can't isolate my exponential expression. And instead, I'm going to jump straight to step 2. I'm going to take the natural log of both sides. Why did I do that? Because it was the direction. Let's not do that. I did it because this is how I get x out of the variable, or out of the exponent, excuse me. So that means I'm looking at x minus 5 times the natural log of 2 is equal to x times the natural log of 0.75 and distribute. Natural log of 2 is a number. if you put it into a calculator, that number is going to be an estimate, and it really just kind of kills everything. So I'm going to leave it as the natural log of 2. So that means I have x times the natural log of 2 minus 5 times the natural log of 2 is equal to x times the natural log of 0.75. All right. Now, I have multiple terms with x, and I'd like to consolidate them. I'd like to put common or put like terms together. So everything with an x is going to go to one side. Everything without is going to go to the other. Everything without an x is already on the left. So all I need to do is subtract that x times the natural log of 2 from both sides. Why is it subtract? Because this is negative 5 natural log of 2 plus x times the natural log of 2. So plus natural log of x natural log of 2 minus natural log of 2. So that goes to 0, which means on the left I still have negative 5 times log 2 and on the right I now have multiple terms. I have x times the natural log 0.75 minus x times the natural log of 2. Now, everything on the right has an x in it. Everything on the left does not. And now I'm going to factor. I'm going to bring that x out. So factor out the x. Because remember, the goal is to solve for x. So factor out the x, and that leaves me with the natural log of 0.75 minus the natural log of 2. So now I have a single x. And that's excellent. That's great news. Excellent news. That sounds like it's a dad joke, and I didn't even mean to. I want x totally by itself. It's currently being multiplied by the natural log of 0.75 minus the natural log of 2. Well, if it's being multiplied by that, then I'll just divide both sides by that. And that will leave me x by itself. And what do I end up with? X is equal to the natural log of 0.7, x is equal to negative 5 times the natural log of 2 divided by the natural log of 0.75 minus the natural log of 2. There's my answer. It does not look like an answer that you've seen before. It doesn't look pretty or nice or neat, but it is B. How do I know? Because I've done this problem before, and I've got some confidence in it. So how do I check this? Same thing. I'm going right back to Desmos, and I'm saying, okay, the left-hand side of the original was x minus 5. The right-hand side of the original was 0.75 raised to the x. And the answer I ended up with was negative 5 natural logs of 2 divided by the natural log of 0.75 minus the natural log of 2. Get that same argument on both sides. And does it work? Yes, it does. The left and the right-hand side agree, which means this is a solution. And that means that my solution set contains a single solution, and that single solution is -5 times the natural log of 2 divided by the natural log 0.75 minus the natural log of 2. One answer, that is the exact answer. Stick with exact answers. All right. Now, if you got confused or bothered because the natural log kept repeating or kept popping up and I was distributing the natural log of 2 like it was a number, check out the lecture video on 3.5, the part 1 of page 1 through 3, and you'll see another way to do this where when I got to this step, when I got to the distribute this natural log of 2, I let the natural log of 2 be the letter C and the natural log of 0.75 be D, and then treated them as constants, as just variables multiplied by C and D, and then we got to the end, and then we just resubbed everything and ended up with the exact same answer. So take a look at that and watch the rest of 3.5.